Hey guys, welcome back to another video. Today we're going to be doing topic 1.11, equivalent representations of polynomial and rational functions. Let h of x equal f of x divided by g of x. If g of c equals 0, then h of x has a vertical asymptote or a hole at x equals c. Example 1, let h of x equal x squared minus 4 divided by x squared plus 7x plus 10. Write an equation for h of x in factored form and find any values of x where h of x has a hole or a vertical asymptote. For example 1, in the numerator, I see that I can do difference of perfect squares. If I take the square root of x squared and 4, I could get x plus 2 times x minus 2. For the denominator, I can do X method. I'm looking for two numbers that multiply to positive 10 and add up to positive 7. Those two numbers would be X plus 5, X plus 2. Okay? I see that I can cancel out these two factors that occur in the top and the bottom. And if I do that, then I would be left with X minus 2 divided by X plus 5. For the whole is whatever I cancel out, and if I set it equal to 0, I would get a whole at x equals negative 2. Remember that the vertical asymptote is whatever factors are left in your denominator, so that vertical asymptote would be at x equals negative 5. Now we haven't done domain yet, but let me sketch it here. Not sketch it, let me write it here. The domain of rational functions is all real numbers except the holes and vertical asymptotes. Okay, so on this example, we have one hole and one vertical asymptote. So we would start writing the domain all the way from the left as negative infinity. Now you are going to skip these numbers in order from smallest to greatest. So the smallest one would be negative 5. Now, we don't ever touch vertical asymptotes, so don't ever use a bracket for those. That's always going to be parentheses. Union, whatever you stop with, you're going to start the next interval with. So we're going to start again at negative 5, and then there's a hole at negative 2. Holes are also undefined, so you're also going to use parentheses. And then remember, whatever you stop with, you're going to start the next interval with, and then we're going to finish off with positive infinity. So all real numbers is negative infinity to positive infinity, but we are going to skip the vertical asymptotes and the holes, okay, in order from smallest to greatest. Okay, let's do another example. Let k of x equal x squared minus x minus 12 divided by x cubed plus x squared minus 20x. Okay, in the numerator, I can do X method. I'm looking for two numbers that multiply to negative 12 and add to negative 1. Those two numbers are X minus 4 and X plus 3. Okay, and then in the denominator, I see that my biggest degree is 3, so I cannot go straight into X method without first doing the greatest common factor. All three terms in the denominator share one x that I can factor out, and I would be left with x squared plus x minus 20. Okay, and now two numbers that multiply to negative 20 and add up to positive 1 would be x plus 5 and x minus 4. Okay, now notice that I made sure to carry this x with me. A lot of mistakes that some kids are making is that they'll do the greatest common factor, but then they won't carry it with them. Okay, so make sure that whatever you take out, you take it with you. And then I see that x minus 4 and x minus 4 cancel out. So the most simplified form of k of x would be x plus 3 divided by x times x plus 5. Okay, so what are the zeros? Remember that the zeros are any factors that are left in the numerator after you cancel out the wholes. In my most factored form, the only factor I have in the numerator is x plus 3. If I set that equal to 0, I would get x equals negative 3. Find any values of x where k of x has a whole. Because I canceled out this common factor in the numerator and the denominator, I would get a whole at x equals positive 4. The vertical asymptotes are what you get after you after you cancel out the whole, whatever is left over in the denominator. We have x times x plus 5. That means I have two vertical asymptotes. I have a vertical asymptote at x equals 0 and a vertical asymptote at x equals negative 5. Find any horizontal asymptotes of k of x. For horizontal asymptotes, I recommend that you use the standard equation instead of your factored. It's just a little bit easier to just visually see what the degrees are. In the numerator, my biggest exponent is x squared, and then in the denominator, my biggest exponent is a cube. So remember, for horizontal asymptotes, you're going to use Bobo, Botten, and Eats DC. Here, my exponent is bigger on the bottom, so I know that this is going to be Bobo. Bigger on the bottom, y equals 0 for my horizontal asymptote. Okay? Now, for the domain, remember it's all real numbers except the wholes and the vertical asymptotes. You are not going to exclude the zeros. The zeros are included points. The only thing that is undefined are the wholes and the vertical asymptotes. You're also not going to include the horizontal asymptote because, as you can see, that is a y value. So that's something that would affect the range of the function, but not the domain. The domain is a set of x values. So remember, all real numbers, you start at negative infinity, and you're going to skip the wholes and the vertical asymptotes. Of these three numbers, negative 5 is the smallest, so I'm going to put that one first. Whatever you stop with, you start the next interval with, okay? So I've used this one. Now between these two that I have left, 0 is smaller. And I'll start with 0 again. The last number I have is 4. I start with 4 again, and because I have nothing else I need to exclude from the domain, I am done, and I'll finish off with positive infinity. Okay, and remember, vertical asymptotes and wholes are always undefined, so you always use parentheses for those. Okay, now it says sketch the graph of k of x. So let's start with all the information that we have. I know that there is a 0 at x equals negative 3. So what I'm going to do is go to negative 3 on my graph, and I'm going to sketch a 0. Remember, a 0 is just an x-intercept. Okay. The next thing is a hole at x equals 4. I cannot pinpoint the location of the hole without having the y coordinate. So what I can do is find k of 4. Okay, and you plug that into your most simplified factored form, which is this one here. So I'm going to have 4 plus 3 divided by 4 times 4 plus 5. That gives me 7 times 4 times 9, which is 7 divided by 36. Now, that number is pretty close to 0. It's not close to 1. So I'm going to have a whole at x equals 4, 1, 2, 3, 4, and it's going to be an open circle pretty close to 0. It's not quite the halfway mark, and it's not 1. It's closer to 0. Okay, now we have two vertical asymptotes. One of them is at x equals 0, right down the y-axis. I'm going to label it VA at x equals 0, and I have another vertical asymptote at negative 5. Okay, and then I also have a horizontal asymptote at y equals 0 right here. Okay, the only thing we need to figure out now is, does the graph go up or down on either side of the vertical asymptote? So in lesson 9 and 10, we talked about how to create number lines to figure that out. Okay, so let's start. We're going to have two different number lines because we have two different vertical asymptotes. In the middle of these asymptotes, you're only going to place the number of the vertical asymptote you're trying to figure out. And you're going to pick a number that comes right before and right after that number. So before negative 5, I could pick negative 5.1, and before that I could pick negative 4.9. You don't want to pick whole numbers. You don't want to say negative 6 and negative 4. It is simply too far away. You want to stay really, really close to the vertical asymptote. So what we're going to do is plug it into my factored form. Okay, so my factored form, before I canceled out the wholes, I was looking at this factored form here. If I do negative 5.1 minus 4, I would get a negative number. Negative 5.1 plus 3 would also be negative. I have an x by itself, and my x is negative 5.1, so that'll stay negative. Negative 5.1 plus 5 is also negative, and negative 5.1 minus 4 is also negative, okay? I have 5 negatives. That's going to result in this side being negative. Now let's do the other side. Negative 4.9 minus 4 is negative. Negative 4.9 plus 3 is negative. By itself, negative 4.9 is negative. Negative 4.9 plus 5 is positive, and negative 4.9 minus 4 is negative. Because I have 4 negatives, that's going to be positive, okay? So to translate that to my graph, that means that on the left of negative 5, so this is the left. On the left, I am going down. So on the left of my vertical asymptote at negative 5, I'm going to draw an arrow going down, okay, as such. And then it said that on the right of negative 5, I'm going up, okay? So on the right of this, I'm going to draw a line going up. Let me draw it a little bit better. Okay, now let's see what happens at 0. I'm going to pick negative 0.1 and positive 0.1. And we're going to plug it into the factors again. Negative 0.1 minus 4 is negative. Negative 0.1 plus 3 is positive. Negative 0.1 by itself is negative. Negative 0.1 plus 5 is positive. Negative 0.1 minus 4 is negative. I have 3 negatives, and an odd number of negatives will stay negative. 0.1 minus 4 is negative. 0.1 plus 3 is positive. 0.1 by itself is positive. 0.1 plus 5 is positive. 0.1 minus 4 is negative. I have 2 negatives, and an even number of negatives will be positive. Okay, so that means that on the left of 0, I'm going down. So I can draw an arrow on the left of this vertical asymptote at 0 going down. On the right of 0, I am going up. So on the right of this vertical asymptote, I'm going to be going up. Okay, so now we're just going to fill it in and connect it to everything else we have. Now on this side, there is no way that this graph is going to cross the horizontal asymptote, but I know that this graph is going to have to curve because I know that rational functions approach the horizontal asymptote all the way to the left. So I can graph this and make it curve so that it approaches the horizontal asymptote all the way to the left. Now in the middle, I see that I have a point at x equals negative 3, and I can use that point to connect these two lines that I had created on either side of the vertical asymptotes. And then on the last section, I can connect this line down to the hole I had made. I don't want to draw through the hole, but I'm going to skip over it, and then I know that, again, rational functions approach the horizontal asymptote all the way to the right. Okay, so that is what the sketch looks like. Let's go on to the next page. Okay, now we're going to be working backwards. Instead of them giving us an equation and we make the sketch, they're giving us the graph and we got to make the equation. So the graph of the rational function f of x is shown above. Write an equation in factored form for f of x. Okay, what I'm going to do is locate all of the features that I see that I know go into the equation. Okay, so starting off, I see that we have a horizontal asymptote right here at y equals negative 1. Now, horizontal asymptotes, those go on the outside of the equation. Okay? We have a vertical asymptote at x equals 2. If my vertical asymptote is at x equals 2, then my factor has to be x minus 2. And the vertical asymptote is always on the bottom of the fraction. It's always in the denominator. Okay? Another thing I see is a hole. And this hole is at x equals 1, 2, 3, 4. So that means that the factor needs to be x minus 4. And for it to be a hole, it needs to be on top and the bottom. It has to be on both so that they actually cancel out and create a hole. Okay? Another thing I see is a 0. Remember that a 0 is just a x-intercept. So I have a 0 at x equals 3. That factor would be x minus 3, and zeros occur in the top of the fraction. They are always in the numerator. Okay, I don't see anything else, so we are ready to put this function together. Okay, so f of x is going to be equal to, remember rational functions are always fractions, so I have my fraction bar. We said that on the bottom, I need an x minus 2. Sorry, I forgot the horizontal asymptote needs to be on the outside. I'm going to put a negative. I don't need to put -1 because 1 times anything is whatever you multiply it by, but the negative is important, so I'll put the negative. And then on the top and the bottom, we said we needed to have x minus 4. And we also said that in the numerator, we needed to have x minus 3. Okay, so that would be the final answer right there. And yeah, pretty easy to do. You just find all the stuff you have and put them in the order that they're supposed to be in. Okay, let's try another one. All right, let's see, we have a horizontal asymptote at y equals 0. Okay, I have a vertical asymptote at x equals 0. I have another vertical asymptote at x equals 1, 2, 3. Let's see, so for the vertical asymptotes, I have one at x equals 0. So the factor for that would be, x minus 0 or something, which is just x. You don't need to put x minus 0 or x plus 0, and the x needs to be on the bottom. We also have a VA at x equals 3. The factor would be x minus 3, and this would also be at the bottom. Okay, I see that we have a hole right here. The hole is at x equals 2. The factor would be x minus 2. And the hole always needs to be on the top and the bottom so that they can cancel out. Okay. I also have a 0 at x equals 1. The factor for that would be x minus 1, and that is only supposed to show up in the numerator. Okay. Now, you might be wondering, why didn't we say anything about the horizontal asymptote? I said that was supposed to be on the outside. And yes, it is on the outside when it is each DC. Okay, so remember that each DC is when the exponents are the same and you divide the coefficients. So here we had 2x's on the numerator, 2x's in the denominator, so it is each DC. They're the same on the top and the bottom. And then from there you divide the coefficients. Now all of these are coefficient of 1, so we would just have y equals 1 times 1, which is 1, divided by 1 times 1, which is 1. So the only way to have it to be -1 is if I put a negative out in the front, which I did. Okay, now if it's bobo, for y equals 0, you don't need to worry about the coefficients because all the bobo talks about is if you have a bigger degree in the denominator. Okay, so you don't need to worry about that if it's at y equals 0. So let's put the function together. F of x equals, start with your fraction bar. We said that we need to have x at the bottom by itself, and we also need to have x minus 3 in the bottom. We said that the whole is at x minus 2, which needs to appear in the top and the bottom, and the 0 at x minus 1 should only occur in the numerator. So this is the function that we have so far. Now, the only thing that we haven't talked about yet is what happens if the graph, is below the x-axis. So notice that if I zoom in here, you see how on the right side, the graph is underneath the x-axis. So that's going to let you know that your leading coefficient has to be negative. So I'll make a note of that. Because the graph is below the x-axis on the right side, the leading coefficient must be negative. Okay, so this is kind of similar to what we talked about on lesson 6. So remember on lesson 6, we figured out you do the right side first. If your leading coefficient is positive, then you go up to positive infinity. And if your leading coefficient is negative, then on the right side, you go down to negative infinity, right? So it's kind of similar here because you're below the x-axis, your leading coefficient has to be negative. So let me graph this for you so you can see. Let me pull up my graph, and I'm going to graph what we thought was the answer before I told you about the negative leading coefficient. So we had x minus 1, and we had, x minus 2, x minus 1, and then, let me see, I think I can split this so we can see both of them at the same time. Okay, this is better. Okay, so we had x minus 2, x minus 1, and then in the denominator we had x minus 3, and x minus 2. Okay, so this was our answer. Let me graph it. So notice that it looks similar to the one that I showed you, but it's not exactly the same. So you can see that on the one that I graphed on red, if you look only at the right side, we are above the x-axis. So that's because we left it as a positive leading coefficient. Okay, but if I were to come out here and put a negative in the front, like I suggested, now the graph is exactly the same, and you can see that on the right side, we are below the x-axis. So by adding a negative, it changes what happens on the end behavior. So again, if I take this negative off, now, so you see how on the left, it's above, and on the right, it's below. If I take off the negative, the opposite is true. On the left is below, and on the right, it's above, which is not what we wanted. So for that reason, this one is going to have a negative leading coefficient in the front. Sorry, this should have been g of x. All right, so let's keep going. Recall that if given a rational function, if the degree of the numerator is 1 greater than the degree of the denominator, then a rational function has a slant asymptote. So we talked about this on lesson, I think it was lesson 7. When we talked about Bobo, Botan, and HDC, we kind of touched on the topic of slant asymptotes, and then I told you soon enough we will figure out how to find the slant asymptote. So if you look at this example, we have things that we've been talking about. We have the vertical asymptote down here at x equals, we have a vertical asymptote at x equals -1. We have a whole at x equals 2. And then what we don't have is a horizontal asymptote. Horizontal asymptotes look like this. Notice that on this one, what we do have is a slant asymptote, which literally looks like a diagonal line. So we have a slant asymptote here. Okay, so that's what they look like. The function k of x equals x cubed minus 4x divided by x squared minus x minus 2. It factors into this. It's graphed above. There's a whole at x equals 2, a vertical asymptote at x equals -1. It does not have a horizontal asymptote, but it does have a slant asymptote at y equals x plus 1. Since the degree of the numerator is 1 greater than the degree of the denominator, we know that k of x would have a slant asymptote. And to find the equation of a slant asymptote, we will use long division. So again, if you look at this, you have x cubed as the biggest term in the numerator and x squared as the biggest term in the denominator. So this would be a case of bottom, meaning that there is no horizontal asymptote. And if you subtract the exponents, 3 minus 2 is 1. And if it's exactly 1, then there is a slant asymptote. Okay, so now let's practice long division so you can actually calculate what the slant asymptotes are. If f of x and g of x are polynomials, then f of x divided by g of x is equal to g of x times q of x plus r of x, where q is the quotient, r is the remainder, and the degree of r is less than the degree of g. Okay, now let's practice old method numerical long division from elementary school. 676 divided by 21 is the same thing as saying 676 divided by 21. You set up your division, the denominator goes on the outside, the numerator goes on the inside. Now, you can't just do 676 divided by 21. I mean, you could if you're good at number sense. So what we do is go number by number, see how we can break it down. Now, 21 does not go into 6, but it does go into 67. So then you figure out 21 times what gives me 67, and the biggest number there would be 3. Then what you do is multiply 21 times 3, and you get 63. Okay, to move on to the next step, I'm going to change the sign. So instead of positive 63, I'm going to make it a negative 63 so that I can subtract and get 4. At this step, I bring down my 6, and then I repeat. 21 times 2 is the closest thing I can get to 46, and that gives me 42. Again, I change the sign and I subtract and I get 4. Okay, now I can't keep going anymore because 21 is bigger than 4. So my quotient is whatever I have on the top, which is 32, and the remainder is 4. To write the answer, you do the quotient plus the remainder divided by the original denominator. Okay, so again, this is the remainder divided by the denominator. And then don't forget the denominator was 21. Okay. In elementary school, you could have been taught to keep going by adding a decimal, adding a 0, bring down the 0, and then you keep going and get decimals. But this is the same thing, just in fraction form. Okay, now let's do the new method of polynomial long division. Okay, so the process is the same. You start off with doing your division, and you put the denominator on the outside, and on the inside, the numerator. Okay, now you want to figure out what is the biggest term on the inside and the outside. On the outside, the biggest term is 2x, and on the inside, the biggest term, meaning it has the highest degree, is 6x squared. So I want to figure out 2x times what gives me 6x squared. I know that that has to be 3x. Okay, so I'm going to put a 3x at the top. Now what you're going to do is 3x times this. But that's a little hard, so you can do it one step at a time. Let's do 3x times 1. That gives me 3x. I'm going to put that underneath the other term that also has 1x so that I can combine my like terms later. Now I'm going to do 3x times 2x. That is 6x squared. The next step, just like here, I changed the signs to negative. I'm going to do the same thing here. But it's not always going to be negative. It's going to be the opposite of whatever it was. So if they were both positive, I'm going to make them both negative. If they were both negative, then I'm going to make them both positive. Let's say this one was positive and this one was negative, then I would make this one positive and this one negative. So you're just switching the sign of whatever it was. It's not always going to be negative. So anyway, so I'm going to switch the sign. I'm going to make both of them negative. Now, if you do it right, these both should always cancel out. 6x squared minus 6x squared is 0. 7x minus 3x is 4x. And just like the other side, you always bring down whatever you haven't used yet. Okay? And then you repeat the process. The biggest term on the inside is 4x. Okay? So you're trying to figure out 2x times what is going to give you 4x. So 2x times a positive 2 gives you 4x. So I'm going to do plus 2 up here. And now we're going to do plus 2 times both of these. Okay? So positive 2 times positive 1 is positive 2, and I'm going to put that underneath the other constant term. Positive 2 times 2x is a positive 4x. Okay? The next step is to change the sign, so I'm going to put negatives in front of both of them. These two equal 0, and 6 minus 2 equals 4. Okay, so the quotient is 3x plus 2. The remainder was 4, and the answer would be 3x plus 2 plus 4 divided by the original denominator, which was 2x plus 1. Okay. Let's do another example. We're going to let h of x equal 6x squared plus x plus 5 divided by 2x plus 1. Use long division to find an equation for the slant asymptote. Now, they don't have to give you this information, okay? If they just say find the equation for the slant asymptote, you need to know that the method to do that is long division. Okay, so let's see if there even is a slant asymptote, because they could be trying to trick us here. Now, the biggest term on the numerator is 6x squared, and the biggest term on the outside is 2x, and the exponent of this one is 1. So they weren't tricking us. It is bought in. It is bigger on the top, and if you subtract the exponents, it is exactly 1 bigger in the numerator. So there is a slant asymptote. So you will start by putting the denominator, and then you're going to divide that by the numerator, 6x squared plus x plus 5. Okay, so we're trying to figure out, first, sorry, I skipped a step. The biggest term on the outside is 2x, and the biggest term on the inside is 6x squared. So 2x times what is going to give you 6x squared? That's going to be 3x. Okay, so what I'm going to do is place the 3x on the top. And then I'm going to do 3x times 1, which is 3x, and I'm going to place that underneath the other term that also had just 1x so that I can combine them later. And then the next part, 3x times 2x is 6x squared. The next step is to change the signs because they were both originally positive. Now they will both be negative. And then I'm going to cancel this out. X minus 3x is negative 2x, and then I bring down my positive 5. Okay, and then we repeat the process. The biggest term on the inside is negative 2x. So 2x times what is going to give you negative 2x? The only number that you can multiply by is negative 1. So now we're going to do negative 1 times positive 1, which is negative 1. Negative 1 times 2x is negative 2x. And the next step is to change the signs. They were both negative, so now they will both be positive. These two cancel out, and 5 plus 1 is 6. You cannot keep dividing anymore because the term on the outside is bigger than the term on the inside. Okay, so for the slant asymptote, the equation always starts with y equals and then it is only the quotient that is in the top of your division. For the slant asymptote, you do not add the remainder, and let me show you why. Okay, what I'm gonna do is graph this so that you can see them side by side. Okay, so I'm gonna start by graphing the original equation, which was 6x squared plus x plus 5 divided by 2x plus 1. Okay, so this is the equation that we get. Okay, now if you were to add the remainder, okay, if we were to write 3x minus 1 plus the remainder of 6 divided by the original denominator, which was 2x plus 1, you get the same exact function. Notice how they overlap. There are two functions here, the original and the one with the quotient plus the remainder. That's not the slant asymptote. The slant asymptote is only 3x minus 1. Okay, and if I graph that, you can see that green diagonal line that goes on the end behavior of the rational function. So if you add the remainder, you are actually giving me the equivalent of what you started with. Okay, so they are equivalent in two different formats and two different representations, but the slant asymptote is simply the quotient. Okay, please do not add the remainder, and also please do not forget the y equals. It did say find an equation. If you give this answer like this, it will be marked wrong. Okay, it needs to have the y equals. Okay, so let's try another example. Let g of x equal x cubed plus 4x squared minus 12x divided by x squared plus 7x plus 6. Find the equations for any asymptotes to the graph of g of x. So first we have to factor this. In the numerator, I see x cubed. That means I need to do greatest common factor. They all share at least one x, which I will take out, and I would be left with x squared plus 4x minus 12. And then in the bottom, I have x squared plus 7x plus 6. Okay. Now I can do x method. Now don't forget we factored out an x, so make sure you put that x there before you do x method. Okay, so two numbers that multiply to negative 12 that add up to positive 4 would be x plus 6, x minus 2. In the denominator, I can do x method. Two numbers that multiply to positive 6 and add to 1 would be x plus 6 and x plus 1. Okay, notice that these two cancel out. So what I would be left with is x times x minus 2 divided by x plus 1. Okay, so now let's find the vertical asymptotes. The vertical asymptotes is what you have remaining in the denominator after you cancel out the wholes. So I have a vertical asymptote at x equals negative 1. For the horizontal asymptotes, again, I recommend that you look at the standard form that was given to you when you started because it's easier to see the exponents. In the numerator, the biggest term was x cubed, and in the denominator, the biggest term was x squared. This is a case of bottom. It is bigger on top. That means there is no horizontal asymptote. Could there be a slant asymptote? Let's subtract the exponents. 3 minus 2 is 1, so yes, there is a slant asymptote. Okay, now we have to do long division to find it. So we're going to do x squared plus 7x plus 6 divided by x cubed plus 4x squared minus 12x. The biggest term on the outside is x squared and on the inside is x cubed. So you're trying to figure out x squared times what gives you x cubed. Well, the only thing I can put there is x. X squared times x is x cubed. Okay, so now I'm going to multiply this x by each of these terms. This time we have 3. Starting with 6, okay? X times 6 is 6x. I'm going to line that up with the other term that only has one x. X times 7x is 7x squared. X times x squared is x cubed. Now we change the signs. Now they're all going to be negative. Okay, these two cancel, they equal 0. 4x squared minus 7x squared is negative 3x squared, and this is negative 18x. Okay, now the biggest term is negative 3x squared. So x squared times what gives you negative 3x squared? The only option there would be a negative 3. So I'm going to put a negative 3, and we're going to multiply negative 3 again by these three terms on the outside. Negative 3 plus 6 is negative 18. Now, I don't have a spot for just a constant number, so I'm going to put it by itself on the side. Or if it really bothers you, on the previous one, you could add plus 0 because there was 0 constant, so adding a plus 0 doesn't change anything. Okay? And negative 3 times 7x is negative 21x. And negative 3 times x squared is negative 3x squared. The next step is to change the sign, so I'm going to make them all positive. These two cancel out. Negative 18x plus 21x is 3x, and then plus 18. The biggest term now on the inside is 3x, but 3x is smaller than x squared, so I cannot keep dividing here. Okay, so my slant asymptote will be at y equals x minus 3. Okay, let's move on to example 8. Let d of x equal 2x times x plus 4 times x minus 1 divided by x squared minus 2x plus 1. Which of the following about the graph of d of x is correct? And then I see that it's asking me, do they have one horizontal asymptote, one whole, one vertical asymptote, one slant asymptote, etc. So they're basically wanting me to find all of the key features of this rational function. So that's what we will do. Before you find the wholes and the vertical asymptotes, though, you do need to factor. So the numerator is already in factored form. I can tell because it has the parentheses, but the denominator is not factored, so I will need to factor that one. So let's say I have d of x equals 2x times x plus 4 times x minus 1 divided by, and now I'm trying to figure out two factors that multiply to positive 1 and add up to negative 2. Those numbers would be x minus 1 and x minus 1. Okay, now notice that I have two of the same factors in the denominator. What I can do is rewrite this as x minus 1 squared. Okay, now let's see. I have two x minus 1s. Okay, I have two of them in the bottom, but I only have one of them in the numerator. So remember, when the same factor, the common factor, has a higher degree in the denominator, then you have a vertical asymptote and no whole. Okay, so on this one, I have no whole, and I have one vertical asymptote at x equals positive 1. Okay, so I can eliminate some answer choices. I'm going to eliminate the one that says there is one whole. So that eliminates A and C. And then it says, this one says we have two vertical asymptotes, but we know that we only have one vertical asymptote. So that leaves us with answer choice D. We said there was no wholes and only one vertical asymptote. And then this says that we have one slant asymptote. Let's see if that is true. So in the numerator, we can multiply this to figure out what the leading term would be. You don't need to multiply out the whole thing unless you want to, but you only need to do the biggest terms of each factor. So 2x is by itself, that's one factor. Between x plus 4, x is bigger, and between x and negative 1, x is bigger. So if you were to multiply these, you would get 2x cubed. Okay, and then at the bottom, it is in factored form. So you don't do this if it's in standard form. If it's in standard form, you just grab the biggest term, which is x squared. And 2x cubed divided by x squared would be bought in. It is bigger on the top. And if you subtract the exponents 3 minus 2, you do get 1. So everything about answer choice D is correct. Okay, now let's move on to example 9. We're going to sketch a picture of the rational function f of x with the following properties. Okay, what I'm going to pay attention to is what it is telling me underneath the limit statement. So this one says as x approaches infinity. I know that as x approaches infinity, I am going all the way to the right. And it's telling me that my y values are going down to negative infinity. Okay, for the next one, it says as x approaches negative infinity. Negative infinity is all the way to the left, and all the way to the left, it says that my y values are going up. Okay, next we have x approaches negative 1 from the left. Okay, and then my answer is negative infinity. So my y values are going down. Now, the only options I have for underneath the limit to be a number is a whole or a vertical asymptote. And remember that wholes always have a y coordinate as the answer. So it would be like, let's say, -5, -5. But we don't have a numerical digit. Excuse me. Okay, so we don't have a numerical digit as the answer. It's not both like -5, -5. What we have is infinity and infinity, which lets me know that this is talking about a vertical asymptote. There is a vertical asymptote at x equals -1, and this is from the left side of the vertical asymptote that the y values are going down. Okay, now we have another limit statement as x approaches -1, it's also going down. So this must be talking about the same vertical asymptote that is at x equals -1, but this side is from the right, and again, it is also going down. So what I'm going to do first is just kind of draw and see if I can put the pieces together. Okay, so all the way to the right, we said that we are going down. So all the way to the right side, I can draw an arrow going down. Okay, we'll connect the pieces later. All the way to the left, we are going up. Okay, now for statement 3 and 4, I know that there is some kind of vertical asymptote at -1. So I'm going to sketch a vertical asymptote at -1. And then we said that on the left of -1, we are going down. And we said that on the right of -1, we are also going down. Okay, so that's kind of how I put all of these pieces together. I just broke it down, try to figure out, is it talking about the left, the right, the vertical asymptote, the whole, does it go up or down, etc., etc. So I hope that makes sense. And now all that I'm going to do is put all the pieces together. So this one here has to connect to that one down here, so it'll look something like this. Now both of these are going down, so that one would have to look something more like this. Now again, this is a rough sketch. It's not going to be perfect. But what happens is whenever you are going all the way to the right and all the way to the left and your answers are either negative or positive infinity, what that means is that these two are referring to a slant asymptote. Okay, so on lesson 7, we talked about if it's a horizontal asymptote, like let's say it was each DC, and you divided the coefficients, and let's say you got -2, then that -2 would be your answer for the left and the right. This is if it was a horizontal asymptote. Okay, or if it was bobble, then your answer would be 0 for the left and the right. The only way that all the way to the right and all the way to the left you're going to get negative or positive infinity is if you have a slant asymptote. So I could visualize where the slant asymptote would be here. It would be somewhere like this, running diagonally along the left and the right of the graph, which is the end behavior. Okay, so that is the slant asymptote there. And again, if we had the equation, we could do long division and see what the actual equation for the slant asymptote would be. Okay, now let's move on to Pascal's triangle and the binomial theorem. Expanding expressions of the form a plus b to the power of n can be tedious. Let's expand the expressions x plus 3 squared and x plus 3 cubed. Anything squared is being multiplied by itself. So x plus 3 squared is the same as saying x plus 3 times x plus 3. Now I'm going to do box method. If you prefer to do FOIL, you are more than welcome to do FOIL. Okay, I'm going to do x plus 3 times x plus 3. I get x squared, 3x, and positive 9, and then I have to combine my like terms. So my answer here would be x squared plus 6x plus 9. Okay, now let's do x plus 3 cubed, which is the same thing as multiplying x plus 3 by itself 3 times. But we did already do it 2 times, right? So it's kind of the same answer as what we had earlier. So all we need to do is multiply it one more time by x plus 3. Because we already did x plus 3 times x plus 3, we just got to multiply it one more time by x plus 3 to make it x plus 3 cubed. So now we're going to do another box method, but this time it's going to be more of a rectangle instead of a square, and you're going to add an extra column, x squared plus 6x plus 9 times x plus 3. You get x cubed, 6x squared, 9x, 3x squared, 18x, and then you get 27. You combine your like terms. These two are like terms, and these two are like terms. So then this is going to be equal to x cubed plus 9x squared plus 27x plus 27. Okay, so these were the answers when you squared the factor and when you cube the factor. Okay, now it wasn't that difficult, but what if we wanted to expand the expression x plus 3 to the power of 7? Are you going to sit there and write it out 7 times and multiply it over and over and over again? As you can imagine, this would be very tedious and time-consuming using the method from above. Fortunately, there is a great mathematical property and tool to make this process much easier for us, and it is called the binomial theorem. So binomial, the word bi means two. What that means is that we're going to have two terms. We're going to have a plus or minus b. And then you're always going to have a degree, which is n. Okay, now this looks very intimidating and complicated, but in reality, it is easy to understand if you can remember a few details. So the first parentheses, we're going to be finding the coefficients using the Pascal's triangle in a minute. But in the Pascal's triangle, you're always going to have the value of n be the number on the top. Okay, and then you're going to multiply all of that by a and b. Now, we do have a term missing here that I want you to add right here. I want you to do b times 0. And then on this side, I want you to add a to the power of 0. Okay, so then what happens is that after the coefficient, you're always going to have a times b. Okay, a times b, a times b, a times b, a times b. Okay, so those things are never going to change. On the top of the coefficient, you're always going to have n, and then that parentheses, that is always multiplied by a times b, a times b, a times b, a times b, etc. The only thing that's changing are the exponents of a and b. Okay, and then the numbers down here, which go up by 1. Okay, so the first exponent of a will always be n. It'll always be equivalent to your degree. And then when you stop, your n will line up over here. So let's say it was degree 4, then you would stop when they were both 4. And then the degree of b will also stop with n. Okay? It looks really confusing at first, but it's really not, I promise. Let me give you some more tricks. So again, these always go up by 1, 0, 1, 2, and you just keep going until you get the degree. So let's say it was degree 4, then you would do 0, 1, 2, 3, and then you would stop at 4. Okay, so those go up by 1. For the degree, again, let's say this was 4, and so then this would also be 4. The next power of a is n minus 1, which would be 3. N minus 2 would be 2. And then we have 1, and then we have 0. So those go down by 1. 4, 3, 2, 1, 0. For b, you go up by 1. 0, 1, 2. Let's say this was 4. So then 4 minus 1 would be 3. And then let's say n was 4. So it would be 0, 1, 2, 3, 4. So it's really not that bad. And then another thing that can help you is to recognize that these two, the first and the last things that you're changing, are always the same number. So 1 and 1, these are always the same. 2 and 2, those are always the same. And then even on the last one, you can see that when you get to the last one, these two are going to be the same. Okay, so let's see. So if you remember that 1, when expanding a binomial expression, the a begins with degree n and b begins with degree 0. And then as you expand the binomial expression, the degree of a decreases by 1 each term, while the degree of b increases by 1 each term until the b term has degree n. We can use Pascal's triangle to find the values of the coefficients n choose 0, n choose 1, n choose 2 in our expansion. When you read these, you're going to say n choose 2, or n choose 0, n choose 1, n choose 2. And you're basically just going in order, starting from 0 every single time. Okay, now this is Pascal's triangle. It might look very intimidating, but it's really easy. And you will be expected to recreate this on your own for the AP exam and any quizzes and tests you are given. Remember, you don't get any formula charts or any reference sheets on the test, but it is very easy to recreate. So all you're going to do, I'm just going to ignore this one, and we're going to create our own so you can see how easy it is. So all you do is start off with 3 1s, okay? And in a pyramid shape. And then all you do is add the numbers above to get the next numbers. So here we have 1 plus 1. I'm going to get 2. And then you always start and end with a 1 on either side. Okay? So then you start again. 1 plus 2 is 3. 2 plus 1 is 3. And then you add a 1 on the front and in the back. You start again. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. And then 1 in the front and in the back. Okay? 1 plus 4 is 5. 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 5. And then the ones on either side. 1 plus 5 is 6. 5 plus 10 is 15. 10 plus 10 is 20. 10 plus 5 is 15. 5 plus 1 is 6, and then 1's on either side. Okay, so you can see how easy it was to recreate that. All you're really doing is just adding the numbers together. Okay, now you need to know what row you're supposed to be looking at. To figure out what row, okay, row 1, 2, and 3, it's going to be the second number on this column here. Okay, on this diagonal column. So we have row 4, row 5, row 6, row 7, and this Pascal's triangle, it can go on forever, okay? Because I can keep adding numbers and adding numbers and adding numbers. There is no last row, but it's really easy to keep going. And then the row number that you need depends on what degree you have, right? So if I tell you x plus 3 to the power of 7, then you need to make sure you have at least the 7th row.
If I tell you x plus 3 to the power of 4, you just need up to here. You wouldn't need to complete all of this because you would just need the fourth row. So the number of rows that you're going to need to recreate depends on your highest degree that you're being asked to expand. Now, a key here is that your first number is always going to be the 0th element, okay? So notice that we start with row 0, so you're not counting from 1, this is row 0. And then in addition to that, all of these here are considered your 0th element. You're not counting from 1, even though the numbers are 1, okay? The first number in each row is the 0th element of that row. So when you start counting, you're never going to use this one. I mean, if you do, anything to the power of 0. Remember we talked about that? We said 1 to the power of 0 is 1, 5 to the power of 0 is 1, x to the power of 0 is 1. So if you have anything like, let's say x plus 3 to the power of 0, that will always equal 1. Anything to the power of 0 is 1. So you're not really going to use this one. I mean, that's kind of common knowledge, okay? So you're really going to start at row 1, okay? So this is the 0th element and the first element. For row 2, 0th element, first element, second element. For this row, 0th element, first, second, and third element. Notice that the number of elements is exactly equal to the number of the row. So in row 1, the last number was 1. Then we have 2. Then we have 3. 0, 1, 2, 3, 4. For the fourth row, you have the last number is the fourth element. So you're never going to have more elements than the degree, than the number of the row. Okay? So let's just do some examples. Okay? Let's say, for example, that I want you to find 3, choose 2. Okay? The first 3 tells you what row to look at. So I'm going to go look at row 3. And I need the second element, but you start counting at 0. So this is the 0th element, the first element, and this one is my second element, which would be 3. Okay, let's try another one. Let's do 5, choose 4. I'm going to go to row 5, and I'm going to look for the fourth element, starting at 0, 1, 2, 3, and my fourth element would be 5. Let's do another one. 7, choose 5. I'm going to go to the 7th row and find the fifth element, starting at 0, 1, 2, 3, 4. This is the fifth element, which is 21. Okay, let's do another one. Let's do 6, choose 6. I'm going to go to the 6th row and go to the 6th element, starting from 0, 1, 2, 3, 4, 5, 6. The 6th element is 1. Okay, let's do 4, choose 0. I'm going to go to the 4th element and I start at 0, so my 0th element is 1. Okay, so don't forget, even though it's typed here, I want you to write it again, because sometimes when things are typed, you overlook them when you're looking back at your notes. So start counting at 0 every time. Okay, let's try some examples. So here we have example 10, x plus 2 to the power of 5. You want to start off by always writing a, b, and n. A is always the first term, B is always the second term, and N is always the degree. Okay? Please do not ever switch these around. It's just in order. A, B, N. Okay? So you're going to start, and this gets kind of long, so if you write big, try to write small. If not, you can grab a separate sheet of paper and maybe even turn it sideways so you have more space. Okay? So we're going to start, you always start with the degree, okay? So the degree here is 5, and you always start counting at 0. Remember, you always multiply by x, and you always multiply by b. Now, remember that these two always have to be the same, so I know this one has to be 0. And I know that we always start this one with 5. If you forget that, Another trick is that these two always add up to the degree. So 5 plus 0 is 5. Okay. Now we'll move on to 5. Choose 1 because you count these up by 1. Okay. You always multiply by x. The degree should be 1 less this time, so now it'll be 4. And this one will be to the power of 1. So again, these two are always the same. And then these two always add up to the degree, which is 5. Okay, let's do the next one. 5 choose 2 times x cubed times 2 squared. These two are the same. These two add up to 5. Okay, the next one would be 5 choose 3 times x squared times 2 cubed. These two are the same. These add up to 5. The next one is 5 choose 4 x to the power of 1, 2 to the power of 4. And then the last one is 5 choose 5 times x to the power of 0, 2 to the power of 5. Now it's very easy to make a mistake because it is so long. So what I want you to do before you move on is always confirm that you're actually going up and down by 1 like you're supposed to. Okay, so start with the first set of parentheses. These should go up 0, 1, 2, 3, 4, 5. That's good. Okay, the next thing you want to check is that the second set of parentheses also goes down by 1, 5, 4, 3, 2, 1. Next, check the power of b. 0, 1, 2, 3, 4, 5. Check. Okay. Confirm that these two are always the same. The first one and the last one should always be the same. And then make sure that all of your exponents add up to your degree. In this case, they should all add up to 5, and they do. Okay, so always confirm, because if you mess up even one little teeny tiny number, you risk getting the entire question wrong. Okay, so now from the Pascal's triangle, I'm going to focus on row 5. So when I ask you for 5 choose 0, you're looking at the 5th row at the 0th element, which is 1. Okay, so 5 choose 0 is 1. You cannot simplify x to the power of 5, so I'm just going to put x to the power of 5. And remember that anything to the power of 0 is always 1. Okay, 5 choose 1, you would go to the 5th row and the first element. This is the 0th element, so the 5 is 5 choose 1. Okay, so times 5, x to the power of 4, 2 to the power of 1 is just 2. Okay, 5 choose 2 is 10 times x cubed times 4. 5 choose 3, let's go look up here. 5 choose 3, we have 0, 1, 2, the third element is 10 times x squared, and 2 cubed is 8. 5 choose 4 is 5, x to the power of 1 is x, and 2 to the power of 4 is 16. 5 choose 5 is 1, x to the power of 0 is 1, and 2 to the power of 5 is 32. Okay, now what you're going to do is go back and you're going to simplify by multiplying all of this in between the pluses. So this is going to be its own term, this is its own term, this is its own term, etc. Okay, so if I multiply all of this together, I get positive x to the power of 5. Okay, now let's go to the next term. If I multiply all of these, 5 times 2 is 10, positive 10x to the power of 4. If I go to the next term, I'm looking in between the pluses, by the way. 10 times 4 is 40, so I have 40x cubed. The next term, we have 10 times 8, which is 80, positive 80x squared. Okay, next we have 5 times 16. If you don't know what that is in your head, you can simply multiply by hand. You need to be well versed in multiplication by hand, because remember, a lot of the times you're not going to have a calculator. So 6 times 5 is 30. You bring the 0, put the 0 down, bring the 3 up. 5 times 1 is 5, plus 3 is 80. So this is plus 80x. And then the last term, 1 times 1 times 32 is positive 32. Okay, so our final answer is very long. The higher the degree, the longer your polynomial expansion is going to be. But you get x to the power of 5 plus 10x to the power of 4 plus 40x cubed plus 80x squared plus 80x plus 32. Okay, let's try another one. Let's do example 11. We have a, b, and n is always the first step, okay? A is the first term, b is the second, and n is the degree. You always start with n, choose 0, multiply that by 2x to the power of 4 times b to the power of 0, okay? So remember, these are always the same. These always add up to your degree. And then you move up by 1, so 4 choose 1. 2x cubed times negative 1 to the power of 1 plus 4 choose 2, 2x squared times negative 1 squared plus 4 choose 3, 2x to the power of 1, negative 1 cubed. And then the last term, 4 choose 4, 2x to the power of 0 times negative 1 to the power of 4. Before you move on, make sure you confirm that you did everything correctly. 0, 1, 2, 3, 4. 4, 3, 4, 3, 2, 1, 0. 0, 1, 2, 3, 4. If that all lines up, then you are good to go to the next step. Okay? 4 choose 0 on your Pascal's triangle is 1. 2x to the power of 4. Now, some of you guys would look at this and say, yeah, that's 2x to the power of 4. Well, no, remember that anything to an exponent tells you how many times to multiply it by itself. So this is really 2x times 2x times 2x times 2x, okay? So you would have to do 2x times 2x, which is 4x squared, 2x times 2x, which is 4x squared, and if you multiply these, you get 16x to the power of 4, okay? So make sure that you're doing it correctly, and don't forget to take the power of the coefficient as well as the variable, okay? Anything to the power of 0 is 1. 4 choose 1 from your Pascal's triangle is 4. 2x cubed, okay, that would be 8x cubed. Negative 1 to the power of 1 is negative 1. 4 choose 2 is 6. 2x squared is 4x squared. Negative 1 squared is positive 1. 4 choose 3 is 4. 2x to the power of 1 is 2x. Negative 1 cubed is negative 1. 4 choose 4 is 1. 2x to the power of 0 is 1. Negative 1 to the power of 4 is also positive 1. Okay, so now we're going to multiply. The first term is 16x to the power of 4 if you multiply all of this. Okay, the next term, we have 4 times 8, which is 32, times negative 1 is negative 32x cubed. The next term, we have 6 times 4, 24, times 1 is still positive 24x squared. The next term, 4 times 2 is 8. 8 times negative 1 is negative 8x. And then the last one would be positive 1. And then this would be your final expansion, 16x to the power of 4 minus 32x cubed plus 24x squared minus 8x plus 1. Okay, now the questions are not always going to require you every time to do the full expansion. So you have to read the question correctly. If it says expand, then do the whole expansion. But if the question says what is the coefficient or what is the second term, you could do the entire expansion. There's nothing wrong with that, but it would be a little bit time consuming. Okay, so there is a shortcut if they only want one term out of the many terms that you could possibly have in the polynomial. The process to start is the same. You start by identifying a, b, and n. So we have x, 5, and 6 there. And then remember that the n is always in the top. Remember that a is always being multiplied by b, but they each have their own exponent, and then this number also changes. So remember, we talked about that on this page. The n is always in the top of the first parentheses, and then a and b are always multiplied together after that. A times b, a times b, a times b, a times b. The only thing that changes are the numbers underneath and above, which I have left as a blank. Okay, so this is going to be the setup for the little shortcut. So this is all you really need to remember, is what order they go in. Okay, so now we're going to plug it in. So 6, choose blank. I'm going to just put a blank, and then a to the power of blank times b to the power of blank. Okay, now the question is asking us to find the term that contains x to the power of 4. Now, of these three terms, the only thing that has an x on it is this one. So the only way I'm going to get x to the power of 4 is if I make this also the power of 4. There is no other way I'm going to get x to the power of 4 unless I do that. If the question was cubed, x cubed, then I would make this x cubed. Okay? And then remember that these two always add up to 6. So the other option for the last blank is for it to be 2. And then remember that this one and that one are always the same, so this one also has to be 2. Okay, so then from here, you just simplify, go to your Pascal's triangle. When you go on the 6th row, the second element is 15. Then x to the power of 4 and 5 squared is 25. Now you have to multiply 15 times 25 by hand. Don't get comfortable with having a calculator when you're at home and then you don't know how to multiply by hand on the test when you have no calculator. Okay, so just practice now that you have the time. 5 times 5 is 25. Put the ones down and then add the tens at the top. So 5 at the bottom, 2 at the top. 5 times 2 is 10. 10 plus 2 is 12. Okay, before you go to the next number, add a 0. 1 times 5 is 5, 1 times 2 is 2, and then you're going to add these together. 5, 2 plus 5 is 7, 2 plus 1 is 3. So this is 375 times x to the power of 4. Okay, now the question did say only what is the coefficient. It didn't say provide the whole term. So the final answer here would just be the coefficient of 375. Okay, let's do one more example. So let's do A, B, and N. A is x, B is -3, and N is 8. So you start with N, choose blank, times A to the power of blank, times B to the power of blank, and this time we're looking for x cubed. So I need to put a cube on the term that has x. And because the 2 at the top have to add up to 8, this one has to be 5. And the first and the last one are always the same, so this one also has to be 5. Okay, so then you go to your Pascal's triangle, go to the 8th row. Oh, I don't have the 8th row, so that means I need to add it. 1 plus 7 is 8. 7 plus 21 is 28. 21 plus 35 is 56. 35 plus 35 is 70. 35 plus 21 is 56. 21 plus 7 is 28. 7 plus 1 is 8. And then you always finish it off with a 1 on either side. So this is the 8th row here. So it's very easy to add extra rows if you need it. Okay? And we were looking for 8, choose 5. So I'm going to the 8th row and I'm going to find the 5th element, making sure to start counting at 0, 1, 2, 3, 4. Here is the 5th element. It equals 56. Okay, so here we have 56 times x cubed. And then, oh, how am I going to find -3 to the power of 5? I'm going to need to multiply -3 times -3 times -3 times -3. Yes, this would be easy on a calculator. No, you're not going to have a calculator during the test. So this is the way you have to do it, okay? Write -3 5 times. Then start multiplying. These two equal 9. These two equal 9, and then this one is by itself. These two equal 81. This one is still by itself, so you still need to multiply those two, okay? 81 times 3 would be 3, and then 8 times 3 is 24, but it was negative, so it would be -243, okay? Now we're almost done here. The last thing we need to do is multiply 243 times 56. 6 times 3 is 18. 6 times 4 is 24, plus 1 is 25. 6 times 2 is 12, plus 2 is 14. Bring a 0. 5 times 3 is 15. Bring the 1 up. 5 times 4 is 20. Add the 1, that's 21. 5 times 2 is 10, plus 2 is 14. Then you're going to add these up. You get 8. 5 plus 5 is 10. Bring the 1 up. 4, 5, 6. And then 5, I did something wrong. I definitely did something wrong here. It's right here. I made a mistake. Let me just go back. Let me just erase and start over. Okay. So 6 times 3 is 18. 6 times 4 plus 1 is 25. 6 times 2 is 12. 13, 14. 0, 15. 5 times 4 is 21. 5 times 2 is 10. Plus 2 is 12. 8, 10, 4, 5, 6. 1 plus 2, 3. And then 1. Remember, this was a -243, so it'll be -13,608 times x cubed. But they only wanted the coefficient, so the final answer is -13,608. Okay? So I know this was a lot of information. Let me know in the comments if you guys have any questions. Thank you so much for watching. Make sure to subscribe. I'll see you guys in the next video. Bye.